In our discussion of Rutherford scattering, we failed to ask the question, is the alpha particle moving at relativistic speeds? Should we worry about special relativity in the Rutherford scattering? And it turns out that we don't need to, but it's close. And so we need to review for our scattering things, and in particle physics we'll definitely need to worry about special relativity in all our calculations. So we should review special relativity now. So special relativity was come up, Einstein published it in 1905 to explain how the speed of light, which appears in Maxwell's equations, could be the same independent of observers. And so his two postulates were that the physical law is the same in all inertial reference frames. In particular, electromagnetism, which contains the speed of light in it, the speed at which electromagnetic waves propagate in vacuum, it would be measured the same in all inertial reference frames. So the speed of light is the same in all inertial reference frames. And that leads to some non-intuitive things that are all the things that one knows about special relativity already. So first of all, because the velocity, this one velocity, is the same in all reference frames, space and time are not any longer independent, and we combine them into space-time. And so the mechanism for doing that is to have time as the zero component of some vector containing 4 elements, and then your 3 spatial vectors. And sometimes we call that x0, 1, 2, 3, and we can combine that into a vector notation, an index notation, where we put an upstairs Greek index to mark the fact that there's 4 components going from 0 to 3. It's also nice if we pick units where c equals 1, and I will be mostly using c equals 1 for the rest of this talk. That may seem strange, but it's not really so strange. You might know that the speed of light in nanoseconds and feet is almost 1. So light goes 1 foot per nanosecond, and so in that units, c is 1. We'll often make space-time diagrams where we show t versus x, and the thing that defines the geometry of this new space-time is that the invariant interval between 2 events is measured to be the same by all observers, and that invariant interval is the difference in time minus the distance in space. Again, with the units of time being units where c equals 1. With that defined, we can then define the Lorentz transformation, which is how the coordinates in one coordinate frame will be transformed to another. And so we do that by taking our 4-vector of positions, the transforms ones, the ones that we want to go to, with primes. And we write a column vector like this of the primes, and we do it by matrix multiplication with the Lorentz transformation, where we have this funny set where we have a gamma, 0, 0, and a minus beta gamma. And I will tell you what beta and gamma are in a second. This is for transformation along z. And so we have this symmetric matrix with gammas and betas, and we just do matrix multiplication to go from our unprimed coordinate system to the primed coordinate system. It tells us how the coordinates change. In this calculation, beta is the velocity over the speed of light from going from one frame of reference to another. So in this sense, if the coordinate frame of the primes is moving along the z-axis at a velocity v, then beta is v over c times that, and we calculate the gamma factor by taking 1 over square root of 1 minus beta squared, both defined by the chain from one coordinate system to the other. As an example, if we have one reference frame moving at 3/5 the speed of light, 0.6, in that case gamma is 1 1/4, 5/4. And in this case, then we can calculate t prime equals gamma, which is 1.25 times t minus beta, which is 0.6 times z. And the z prime coordinate will be 1.25 times z minus 0.6 times t. And x prime and y prime are just the same as x and y. Now, we'll use, since spacetime has 4 dimensions, we'll often talk about 4 vectors. And in particular, we've already introduced the 4 vector for position, where we have x mu, like so, and we often write that as t as a 0 component, x, y, and z, where, mu equals 0, 1, 2, and 3 for those coordinates. Now, we also will want to worry about velocity, and so we'll define the 4 velocity, but we can't take the derivative of x with time, because time is not a invariant parameter. We have to use some time-like thing that's invariant, and we can always do that for a particle moving at a constant velocity as the proper time of that particle, which is the time that a clock on that particle would do. So at rest in the frame where the particle's at rest, that clock's time is the proper time, and we call that tau often. Tau, the proper time. And if the particle is moving, then that will often introduce a gamma due to the fact that time is dilated. And so we define the 4 vector, and we usually use u for that instead of v, for the 4 velocity, as the derivative of the position in space-time d tau. And notice that for a particle at rest, then, we'll always have u mu is 1, which is its time, and then it's not moving in space, so the x's are all zeros. But if it's not at rest, then we will get u mu equals gamma, this factor 1 over 1 minus beta squared, and then gamma vx, gamma vy, gamma vz as the 4 velocity. With the 4 velocity defined, it's very easy to define the 4 momentum, p mu. It's just m times the 4 velocity. So just as in Newtonian mechanics, momentum is the mass times the velocity. That's true in special relativity too. Now, we want to define a scalar product as well, something that is just a number at every, that we can define at points in space-time. It's a number, not a thing, an object with components, but we can't define a dot product like we would normally do, because you can imagine that if we had x mu dot x mu, well, that would be x0 squared plus x1 squared plus dot dot dot. And that doesn't make sense because we want to do the invariant interval. And so we define this notation for a scalar product where we take the x mu and we multiply it by a funny object where we put the mu downstairs rather than upstairs, and we define that product to be x0 squared minus x1 squared minus x2 squared minus x3 squared. And we do that by saying that this is the same as a bigger product, x mu times a funny object, x eta mu nu with the things downstairs, and x nu. And when we do this product, we're using Einstein summation notation, where the mu's 1 up, 1 down, get summed over all the possibilities, 0 through 3, and likewise with the news. And that equals, so if we write then the first x as a column, as a row matrix, the eta mu nu as a 2 by 2 matrix, and the second x as a column matrix. Now we're going to do matrix multiplication, and the entries of eta are plus 1 in the first entry, and then minus 1s along the diagonal, and 0s everywhere else. So that the only time you get an entry, so you would have x0 times plus 1 times x0 to give you the x0 squared, and then x1 times minus 1 times x1 to give you the minus x1, and continue in that way. The interesting thing about this is that you can say u mu that is always going to be 1. So all particles always have a squared velocity of 1 unless they are massless particles like speed of light, in which case you can't define this. The momentum scalar product is always going to be the mass squared, because the u squared part of that just gives you the 1, and the m squared just comes through. Now we should say a few more words about energy and momentum conservation in this scheme, and what this new momentum operator is. And in the zero component, so if you have P0, that's going to be the m, and then times u0, but that's just going to be gamma for a moving particle from the zero component of a moving particle's form momentum. And recall that if gamma is 1 over the square root of 1 minus beta squared, and beta is small, we can expand this, and this is going to be m times, so gamma is 1 minus beta to the minus 1/2 power, so we expand 1 minus beta squared to the minus 1/2 using the binomial theorem, and that's 1 plus 1/2, or minus minus a half, beta squared. And you see that that is m, multiplying out the m, by 1/2 m v squared, because beta is just v over c, and we're setting c equals 1. And we see that this is the kinetic energy of the particle, but we have this extra constant to it. So we understand the zero component of the form momentum to be energy. In that case, we can write that, and I'm going to write, so in general, the 4-vector momentum without vectors or without anything, I'm going to write like this, and I'm going to square that. I'm just saying that, this p mu times p mu, we already know that that's m squared, but if I multiply out and do the calculation, I get that this is p0 squared minus p1 squared minus p2 squared minus p3 squared. And I can rewrite that as this is the energy squared minus the 3 momentum quantity squared. So that's the magnitude of the 3 momentum. And we can rearrange this equation then and find that E squared is P squared plus M squared. And note that in the case where there's no, where the particle's at rest, what we have is E squared equals M squared, or taking the square root of that and putting the C's back in, E equals MC squared for a particle at rest. Okay, all that is useful when trying to understand collisions because we can write an equation for a collision now. Let's draw a collision between two particles. So we have two particles coming in, they collide, and two particles come out. That's our normal scattering kind of things that we would have. So let's label this as P1, P2, and they come out with Q1 and Q2. Conservation of for momentum says both energy and momentum are conserved, and we write that as P1 plus P2, mu component of that 4 vector, equals Q1 plus Q2 for momentum of that vector. Now, it's nice if we go to what we would have called the center of mass frame, but that doesn't make sense in special relativity, so we just say the center of momentum frame, where we arrange things such that the spatial momentum components of P1 and P2 go to 0, and what we have is something like P1 like this, and P2 like this. They collide, and you get Q1 and Q2 looking like so. And that defines, so in this case, the P1 plus P2 spatial components are just defined to be equal to 0, the sum of them. This is useful. Now we can also define decays where we just erase the P1 and P2 and say we start with a mass in the middle and out come a Q1 and a Q2. But if we have the center of momentum frame, the mass is sitting there, we have, in that case, m squared of that mass is equal to Q1 plus Q2 for momentums squared.